Last time, we saw the extended Euclidean algorithm, and we saw the first example of a result whose statement mathematically is quite different from the kitchen recipe steps you would have to follow to implement it and get a result or a computation from it. We skipped the part where we proved why this should work mathematically, and I explained how you would use it for to achieve two things. First of all, compute the greatest common divisor between any two pairs of numbers. And second, write this result as a linear combination of the original two numbers. It tells you how to find the coefficients. This will be made, it will be made evident in a few lectures why this is so important and useful. But for now, I want to focus on the mathematical aspect as well. And the statement that makes the extended Euclidean algorithm work is the fact that if you have a number a and you divide it by a number d using the quotient remainder formula, then finding the greatest common divisor between the number you're dividing, the numbers a and d, is the same as computing the GCD for d and r, as you can see as the statement of the theorem, the way I wrote it down. So I'm curious, there's two things to prove when you claim that the GCD is equal to some number. You have to show that that number is indeed a common divisor and that it is the greatest number with this property. So there are like two different statements to prove. But here we're stating that two GCDs are equal to each other. So I'm just curious, maybe you can take a minute to think about how you would prove this if you were given this task. So I will pause this for a few seconds. There's an insightful idea here that is quite important and whose implications will be formalized in the second hour of this lecture. And that is the fact that the quotient is kind of irrelevant for this type of answer. Say you compute it using the division algorithm, the quotient and the remainder. If you had made a mistake in finding the number q, then this wouldn't affect the result. It would be completely unimportant. And there's a reason why this is true. And like I said, we will make this formal using an equivalence relation, the same way that we constructed the integers as a quotient over the natural numbers. There's a hidden structure on top of the integers themselves that can be constructed as a set quotient on them. That is very important. But before we do that, let me tell you perhaps the most significant result of elementary number theory that will save us a ton of time when it comes to studying this important subject. Let me write down the proof and then we can talk about that. So the reason this works is actually quite simple. So we claim as part of the proof, we are actually going to prove something stronger. It's not just the fact that the greatest common divisors between these two pairs of numbers are the same, but I claim that these two pairs of numbers actually have all divisors in common. That let's say S sub A, D, and D, or maybe I should use the letter D for divisor, is the same as the set of common divisors of D and R. So naturally, if both sets are equal, they must have the same largest element. So that it would be enough to prove this, which is of course a stronger statement. It will not always be the case that two GCDs being equal follows from the fact that they have the same common divisors, right? This is just more of a coincidence in this case. Okay, I've got the set of common divisors. is the same as dr. I think the statement is clear. Maybe I could have written it a little bit clearer. Set of common divisors of dr. So let's prove this. What letter should I use? X be a common divisor between A and D. So X divides A, X divides D. How would you argue that X divides D and R? Well, clearly X divides D because it is a common divisor, so the first half is done. Why should X divide R? And for this, you have to remember a very basic property that was covered in the tutorials, what I called quote unquote linearity. And this is quote unquote because I don't know if there's a better name for this. If you've taken linear algebra, this might seem familiar. It's not, I don't know if it's a very standard term, but that's the way that we're going to refer to this phenomenon. And that's basically the fact that if a number divides two integers, it will divide any integers combination, any integer combination of those two integers. And the remainder is an integer combination, right? X divides A, so it must divide A minus D times Q, which is an integer combination of A and D. But this is R. So X is an element of D R. Conversely, if you take a common divisor to D and R, then, well, X divides D, but also X will divide D times Q plus R, which just happens to be A. So this is actually a very short proof, but it contains an interesting trick that you might want to remember because it is quite useful. Okay, so one consequence of the extended Euclidean algorithm, by the way, I didn't prove the whole algorithm. I didn't prove to you that the algorithm always works, that it terminates, that it halts in a finite number of steps, but I will leave those details up to you since that's more related to computer science than math, and I did explain why mathematically the argument is sound. But there's a different way of proving that the greatest common divisor can always be written as a linear combination of the elements. So I will prove that in a little bit more generality, and I will add some extra spiciness to it that will actually save us a ton of time. Especially if you've taken this course before, you will know that getting to the fundamental theorem of arithmetic can be quite cumbersome and requires a long series of lemmas, where I claim we only need two intermediate results. Okay, so the following fact about the natural numbers, not the integers, is equivalent to the fact that induction or equivalently recursion works. And this is known as the well-ordering principle. From a set theoretic perspective, this is the underlying fact that makes all of these principles work. It is so fundamental that I cannot prove it to you without using something like induction itself. And the way you would justify induction working is using this principle. So the argument is kind of circular, but if you want to understand why this is not a problem in our case, then I suggest you go back to, I think it was lecture number 2, where I talked about what was it, the Baron Münchhausen, right? And this anecdote of him lifting himself up, including his horse, from a swamp that he was stuck in. Anyway, so the claim is that every non-empty set of natural numbers has a least element. And keep in mind that this statement is, of course, not true for the integers, right? The integers themselves are a non-empty set of integers that doesn't have a least element. And there's infinitely many such subsets of integers that don't have a least element. But the natural numbers are special. And this is perhaps the most special, the most important fact about the naturals. So why don't we prove this just as an exercise so that we can practice our skill? Okay, I have a question in the chat. Does least mean smallest? Yes. least element, minimum element, smallest element, first element. Those are all synonyms. And in the case of linear orders like this one with trichotomy, then minimal element is also a synonym. So yes, thank you. That's a good question. Maybe I should add that as a comment. Least element, first element, minimum, smallest. And I think those are the basic synonyms, yes? But that's a good question. Sometimes there's subtle differences between these words. This is not such an example. Okay, so how would we prove that this is true? I claim I can prove this to you using strong induction. So let's write down the proof. Let's see. By contrapositive, I'm combining two proving techniques into one proof, right? So contrapositive means I am going to flip the implication around and prove the negations instead. So what I have to assume that S, or whatever you want to call it, is a subset of the naturals with no least element. And this is just a comment, so let me change the color. The thing we want to show is that S must be the empty set. Then by contrapositive, if you have a set that is not empty, well, then it must have a least element, right? So does the way this is set up make sense? Write this down. Want to show. Okay, so I will prove this fact to you using strong induction. Strong induction is a technique used to prove properties about natural numbers. So to show that a set is empty, it would be enough for me to convince you that every natural number has the property of not being in S. Actually, let me write that down. That is for all natural numbers. That natural number is not an element of S, right? That's the classic way that induction proofs are set up. You want to prove that something is true for all natural numbers. So let's prove that the first natural number satisfies this. So notice, so 0 is the smallest element, the first element of the natural numbers. So if S has no least element, well then 0 cannot be an element of S, because if it were, it would be the smallest element of S, given that it is the smallest element overall of all natural numbers, right? If you have the smallest element of everything in your set, well, the only candidate for being the smallest element of your set is that element itself, right? So 0 is not an element of S. In other words, I verified this property for the base case. Now, just to be a bit extra clear, what would be the inductive hypothesis for this type of proof? And I'm writing this in green because while I strongly encourage you to keep track of this mentally and maybe write it down if it helps clarify a proof, this is not an essential part of the proof in the sense that removing this will not yield a problem, will not incur in some fallacious argument or flawed logic or something like that. So what is the inductive hypothesis? I'm claiming that, let me think about this, for all, you take a number n and you claim that for all numbers smaller than it, right? The strong inductive hypothesis is assuming not only that the previous element has the property, but all previous elements have the property, all predecessors of n, right? So for all n, k is not an element of S because that's the property that we're trying to verify. So we want to show by strong induction is that n has the property, meaning it's not an element of S. But you can see why this is true, right? So here's a question for you. Could n be an element of S? What would happen if n were an element of S? Body inductive hypothesis. Okay, I'm seeing some things in chat. Exactly. Okay, okay. So I'm guessing this is familiar to at least some of you. So maybe I don't have to stop adding so many comments. If n were an element of S, given that nothing below n is in S, that would mean that n has to be the smallest element because there's nothing smaller than n that's a member of S, right? So n would be the smallest element, which contradicts the choice of S. By choice of S, of course, I mean the thing we're assuming about S, which is that it has no least element. So this is not true. So n cannot be an S. So by induction or strong induction, S is empty and we're done because this by contrapositive implies the fact that every non-empty set of naturals has a least element. So this is sort of an intermediate result, but it is very useful. Every proof that I've ever written down that uses any type of induction can be rewritten to use this principle instead, because this principle is the core truth behind all of those proving techniques. The fact that recursion works is this principle. The fact that if you code a program and you write down the base case and then you make the function call itself, the fact that that works and produces the correct result that you would expect is because of this principle. And all of these principles are equivalent, but if you're curious and want to learn about something that is actually stronger than this, then you should look up something called transfinite induction. That is a technique that is actually different and more powerful than this one. So here's the next statement that I want to prove. Let's take a few minutes to understand it. I think this is the last thing. Okay. So this is known as Bézout's identity. Historically, this was discovered way after Euclid, way after all of these classic results. This is quite important. You'll see that the proof is not that complicated, and we are going to shortcut half of number theory using this result. So this is quite important. Every time you hear about co-prime numbers, the first thing that should pop into your head is using this identity, because indeed it's like a bit of a hack, you know, a bit of a theoretical hack. So the statement reads as follows. You take a bunch of numbers, a bunch of natural numbers, let's say, and not all of them are zero. Let me add this as a comment, right? So this simply means not, this is an abbreviation of the phrase, not all AIs are zero. Some of them could be zero, maybe none of them are zero. The only case I'm excluding is all of them being zero. And why do you think that is the case? Why do you think it's important that not all of these numbers are zero? And why am I allowing the possibility of some of them being zero? And the claim of the theorem is that the greatest common divisor between these k natural numbers coincides with the smallest positive linear combination of them, right? If you're into linear algebra, if you've taken that course before, well, this is no different than the span. This is like a restricted span of these vectors in a way, right? So is the statement of the theorem clear? And why do you think it's important that these AIs are not all zero? Why would that cause problems? The reason that I have to exclude this possibility is because you cannot define the greatest common divisor of a bunch of zeros, right? Everything is a common divisor for zero because zero is the biggest, the maximum element in the divisibility order, right? So if I ask you what is the greatest common divisor between 0, 0, and 0, then you cannot answer that question because every number is a common divisor. So there's no greatest common divisor, right? You need at least one of the numbers to be non-zero so that it only has a finite number of divisors of which you can take the maximum. Similarly, the set that I wrote down on the right side of the screen, the statement, maybe let's call this something, call this S again. We'll call this set S. The set S would have no least element, right? Because if all the AIs are zero, there is no positive linear combination. The only combination you can get out of them is zero. So there's no least positive linear combination. So there's two reasons why we need that, but I claim that as long as not all of them are zero, this thing will work. So first, taking all alpha i's, the coefficients equal to 1, we see that if you just add up the numbers, these are natural numbers and not all of them are zero, we see that S is not empty, right? Because it contains this sum, right? If I just add up the numbers, I get a positive linear combination. So S is not empty. So D defined as the smallest element of S exists by the lemma I just described, by the well-ordering principle. Keep in mind that when you're proving a statement like this, proving that the statement makes sense in the first place is usually part of the proof, right? I don't just have to show you that these two things are equal. I have to convince you that this minimum exists in the first place, right? If I remove, for example, if I remove this symbol that I'm circling in red, then the statement, I mean, this will not make sense anymore, right? There's no least element in that case. So this is something that is our responsibility to verify as part of the proof. So yeah, let's keep that in mind. Maybe I can squeeze this a little bit. There we go. Okay, so let's call the smallest element D. We want to show that D is the greatest common divisor between all these things. So it seems like there's two things to verify, right? So first, we show that D is a common divisor. And then we show that it is the greatest common divisor. Common divisor, of course, of a 1 dot 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 a k, all these numbers, right? Now, why would that be true? Does anyone have an idea? Since this is kind of tricky. Okay, guys, sorry, I see something in the chat. Okay, that's really good. So the in the chat I'm reading, assume that it's not true and try finding a smaller element of S, contradicting the fact that D is the least element of S. So that's really insightful because that's usually how these proofs work, right? And we could have done all this by strong induction. It would work similarly, but we had to justify that this number exists in the first place. So why not do everything by the well ordering? So first we show that D is a common divisor of these numbers. Exactly. So here's the trick, and this is actually stronger than the statement. So you should pay attention because the proof actually contains more information than the statement itself. This is one of those cases where the proof contains part of a procedure, you know, or stronger statements that are cumbersome to write down, but it will expand your understanding of what's going on. So I will not just show that D is a common divisor of these numbers. I will show that it's a common divisor of everything in S, right? So how do I claim this? Well, take any element of S and keep in mind that this is a stronger statement because the AIs are themselves elements of S. So if I show that it divides not just the AIs but everything in S, Well, in particular, I'm showing that it divides the AIs, right? Stronger, I mean that it seems stronger. Of course, these are equivalent because if a number divides the AIs, it will divide everything in S, given that these are linear combinations of the AIs, right? So it's logically equivalent. It's not logically stronger, just stronger in the sense that it seems like I'm proving something that has more information. Okay, so how do we show that it divides everything in S? We'll take an arbitrary element of S, and we're going to follow the suggestion in the chat of trying to conclude that there's a smaller element, right? So let X be D, let X be an S. So the way this typically goes, if you have no tools, obvious tools to prove that something divides something is, why don't you just try dividing it and see what happens, right? So division, by the division algorithm, we apply the division algorithm, we get two integers qr, and the important thing about r is that it's a remainder, right? So it's non-negative and it's smaller than the thing that you're dividing by. So we're dividing x by d. So it satisfies this, and x divided by d is this. As I've mentioned before, the quotient, we don't really care about it, but we have to write it down because we haven't formalized this idea that we can always or almost always ignore the pesky quotient. So we have this statement, right? Now we do the same trick we did earlier in the proof of the extended Euclidean algorithm, right? Which is solve for r. Now here's something interesting. I claim that this is, okay, maybe I should actually, I think I will have to write this down. So if I want to tell you what R is, maybe I should give these elements a name, right? So since D and what's the other name? What was it? D and X are elements of S. There exist coefficients that tell you how to produce these numbers as linear combinations, right? So there exist, maybe you could call this DIs, integers. These are integers, possibly negative integers. And for the x, why don't we just label them xk? Hopefully this doesn't cause any confusion, but it shouldn't. Xk's, these are also integers, such that x is the same as the combination, okay, it's out of the way, is the sum from I to 1 from the xi ai. And of course, what's the other thing? D. D is the sum of the coefficients di, ai, k. It's a bit cumbersome to write down, but I swear this makes sense. Okay, so now that we gave everything a name, we can just substitute, and we get this is the sum from I1 to k. We just have to take into consideration the coefficients for the x, which is the xi, and subtract the coefficients of d, right? And the q's just can be just factored out, right? There's nothing else to do. AI. Actually, sorry, parentheses is wrong. The q comes here, and then comes the AI, right? So notice something interesting. R is a linear combination of the AIs. I'm using the same idea as the previous proof that I showed you, right? The remainder is always a linear combination of the numbers that you're dividing. But here, since the numbers you're dividing are themselves linear combinations, you can use a sort of transitivity to conclude that the remainder itself is a linear combination of the original coefficients, of the original numbers AI. So the question is, this seems like it would be an ideal candidate to be an S, but there's one thing missing, right? There's two things that you have to check before you can conclude that something is an element of S. First is that this is a linear combination, and second is that this is a positive linear combination, right? We don't really know if this is positive or not, so we cannot yet conclude that this is an element of S. But perhaps there's something else going on, and maybe you can tell me why R is for sure not an element of S. So who can tell me why that is? Okay, I see some activity in the chat. That's great. Exactly. Okay, very good. R is smaller than D. If D is the smallest element of S, then R is not in S, right? So since by minimality meaning the fact that D is the smallest element, minimality, R is for sure not in S. But that means, according to the sentence above the one I'm writing in, that it has to be zero because it is a linear combination. So if it were positive, it would be a positive linear combination, thus an element of S, right? So this means that this is zero. Why? Well, because it is a linear combination, right? According to what I just proved. Because it is a linear combination. It just cannot be a positive one because it's not an S. But what does it mean for the remainder to be zero? Well, it means that the numbers divide each other, right? So therefore, not each other. I mean, x is divisible by d, right? So this is dq plus r, which is 0. So this is just dq. So d divides x. In particular, d divides ai because ai is, of course, a linear combination of the ai's, right? ai can be seen as a1 times 0 plus dot 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 plus 1 times ai plus 0 times ak, right? Just set all coefficients equal to 0 except the one that you care about, the ith coefficient, and then you have ai, right? So this is obviously an element of S. And then we're done. We have shown that D is indeed a common divisor to everything, right? We have yet to show that it is the greatest common divisor. How do you think we're going to achieve that? D is smaller or equal than the greatest common divisor, right? Because it is a common divisor, so it cannot be bigger than the greatest common divisor. Since D is a linear combination of the AIs, right? So A1, AK, the greatest common divisor that in particular divides these numbers must divide D, right? Divide D. So the greatest common divisor D divides the greatest common divisor, and the greatest common divisor divides D, but these are natural numbers, so these must actually be equal, right? And that's what we wanted to prove. So there's two insightful things that arise from this situation. Not only the fact that the statement is true, that the greatest common divisor is the least linear, positive linear combination, but also the fact that every divisor must divide the greatest common divisor. Do you see what I mean with that? This proof contains that fact. If you take a bunch of numbers and you find their greatest common divisor, not only is every other divisor smaller than it, but it divides the greatest common divisor, which is a stronger statement. They're not just smaller numbers, they are themselves divisors of the greatest common divisor. Something analogous to this will happen with the least common multiple, which we talked about or mentioned somewhere. We haven't really explicitly talked about it too much. Okay, before I mention some interesting consequences of this, I do need some notation slash definition, some of which you've probably already heard before. So a prime number, and there's two ways of defining this. There's the correct way and the incorrect way. People say that a prime number is something divisible by 1 in itself. I don't like that definition because it doesn't quite explain why 1 is not a prime number. For that, you have to look at the lattice, right? The lattice theory tells you why 1 behaves so differently in this new structure. So a prime is, or a prime number is a natural with precisely 4 divisors, right? With 4 divisors. Maybe I should add 2 positive and 2 negative. Right, so that's how we define prime number. How many divisors does the number 1 have? Well, it just has 1 and minus 1. It has 2 divisors, not 4. So 1 is not prime, okay? The second thing is 2 integers, A, B, are co-prime, also called relative primes. Denoted A. This symbol is usually reserved for perpendicular in geometry, and there's a reason why. There's a way to make sense of the fact that there is something perpendicular happening. If you've taken linear algebra before, there's a way to define vectors using the the exponents of prime factorization. And those vectors will be perpendicular if and only if the integers are perpendicular, coprime. So this symbol makes sense if you're curious. It's not just a random symbol, right? If the greatest common divisor is the smallest it could be, which is 1, right? It cannot be anything smaller than 1. So the least number of common divisor that you could have is just 1, and of course minus 1, right? And I think that's probably all we need. So maybe some examples. I will not give you examples of prime numbers. Maybe I should. 2, 3, 5, 7 are primes. We don't know, right? Right now, we don't know how many primes there are primes. Examples of co-prime numbers is, well, 2 and 3, 3 and 5. Prime numbers are always co-prime, but maybe an interesting example would be 9 and 25 are not co-prime. Sorry, 9 and 25 are not primes, but they are relative primes, right? So this doesn't mean that any of the two numbers must be prime. It just means that they don't share anything in particular. Okay, so someone's asking why perpendicular. So right now, I think it's best if we just assume that this is the symbol that I'm using, and it's not everyone uses this symbol, but I find it a nice way to quickly write down this fact. So one way that you could understand why this is perpendicular, it will make sense when we have the fundamental theorem. But basically, if you have a number and you factor it into powers of primes, right? So something like this, pi p1 alpha 1, p2 alpha 2. This is just to answer the question in the chat, right? So pn alpha, sorry, pk alpha k. Then you could construct a vector using these coefficients for every prime number, right? For every fixed number of primes. And then with this, these two coefficients, sorry, these two vectors are perpendicular if and only if the numbers are co-prime, right? Because perpendicular tells you that the dot product between them is 0. And this means that since these are natural numbers, they cannot have anything in common, right? If one of the coefficients, the exponent is positive, the other one must be 0, right? What is another vector? Okay, so this is slightly out of the scope of what I'm trying to explain, but this is just to justify the notation in case you're interested. Okay, so let's say you take another vector and another prime number, sorry, another number m. And then you can always write it in terms of the same primes, right? And then these two vectors, the coefficients that uniquely determine the integers n and m, these are co-prime if and only if n and m, sorry, these are perpendicular if and only if n and m are co-prime, right? So in other words, these two vectors are perpendicular if and only if these two numbers are co-prime. And that's what justifies the notation, right? It's the same symbol. Perpendicular vectors, and that's it. This is not too important. I don't think we will ever use this in this course, but in case you were curious, that's one way to justify why you can interpret coprimality as a sort of perpendicularity in some vector space that's naturally associated to this. So I will delete this, but hopefully it kind of justifies the notation. It's not that important. Okay, so this is I have defined prime number, I have defined coprime numbers. So here's a corollary of the previous theorem. Corollaries, I guess, that are important. So the first, and this is the most important fact about coprime numbers, is that A and B are coprime if and only if you can find S and T integers such that AS plus BT is 1. Why is this true? Well, A and B being coprime by definition means that the greatest common divisor is 1. That means that 1 is the least positive linear combination of A and B. But in particular, it is a linear combination. So 1 can be written as a linear combination of A and B. This is not just true for coprime numbers, but something that you even know how to find the coefficients of using the extended Euclidean algorithm is that if you have two numbers, then the greatest common divisor is always a linear combination of those two numbers. But in particular, this applies when that GCD is 1 as well, which is an interesting and very, very significant particular case of this. Let's see. If P is prime, and this is another way of defining prime number, by the way. If P is prime and P divides a product, then P must divide one of the factors, right? P divides either the first factor or the second factor. And if you have a product of many numbers, well, it must divide one of those numbers, right? Something that is also very similar is that if A is co-prime with B, if A has nothing to do with B, but A happens to divide something where B is a factor, then it must divide the other number. Sorry, not P, A, right? There's no prime numbers involved here. Now, these two statements, maybe add this in green, these two statements, that's sort of, wait, it's kind of hard to do it this way. These two statements are different, but these are both known independently as Euclid's lemma. Depending on what textbook you're reading, one of these two will be what's called Euclid's lemma. This is known much, much earlier than Bézout's identity. But we're going to prove this using Bézout's identity, and it will save us a ton of time if you believe me. Okay, so maybe let's prove this. There's a fourth property that I don't want to prove because it's a simple exercise on induction, but it's one thing you could use to practice. Is that a number n divide a product is co-prime to a product of, I don't know, what should we index these by? AIs. Something is co-prime to a product if and only if that something is co-prime to every factor. And you can see why this is induction because, well, it's actually a statement on k, on the number of factors, right? And you can do something similar for number 2, generalize this. If a prime number divides a product of k numbers, it must divide one of those k numbers. N is co-prime with AI. This is important. This is important, and you can prove this using all of the techniques I've mentioned. So maybe let's add some comments as to how to prove this, and then we can go on a short break because I think we're done with all the everything we needed for the fundamental theorem, right? So one follows immediately from Bézout. Bézout's identity. Two. Two follows from three. Three is stronger because two talks about prime numbers, but three talks about co-prime numbers. So in particular, it will apply for prime numbers, right? And why this is true, I think the details should be left as an exercise. If this is not evident for you, then you should spend some minutes thinking about why this is true. Maybe during the break you can do that, and you can let me know if you have questions or if there's anything confusing. Let's actually write down a proof for number 3 so that we are actually doing something, right? So how do we prove 3? Since, this is the proof, right? Since A is co-prime with B, by 1, there are integers S and T such that 1 is SA plus BT. Yes. Right? Then I can just multiply everything times C, and I get ASC plus BTC. And what am I trying to prove? I'm trying to prove that A divides C, right? But of course, I can just factor out A from here, right? This is AS. Now, BC is divisible by A, so I can factor out A. In other words, there is a quotient. This quotient is unique, something that I haven't proven to you, but it is easily verified that this notation makes sense even if I haven't defined rationals, right? That's an integer. So another way of arguing why this exists is basically this is the integer defined as the integer with the property that if I multiply it times a, times a, I get bc. Such an integer must exist because a divides bc, and by definition that means that there's something that when multiplied times a is equal to bc. But that's something, well, I can just call it bc over a so that I don't have to do so much notation, right? Does that make sense? This is not a fraction, okay? That's not a fraction. That is not a rational number. That is an integer. I haven't defined or constructed the rationals. And if you don't like this notation, then just do the extra step and call this something else, like x, right? There is some x such that x times a is equal to bc, and then that number that I just wrote down is x, okay? So the conclusion is that A divides C because, well, I literally wrote C as A times something, right? Now, like I said, 4, I think is a good exercise to practice both induction and how to deal with co-prime numbers. So this is a simple exercise that you should take a look at. Okay, let me just state the fundamental theorem. There's no need to do a million small lemmas like some textbooks might suggest before we get to the fundamental theorem, right? This is not necessarily an obscure thing. Fundamental theorem of arithmetic. Perhaps the oldest fundamental theorem known, one of the earliest results in math altogether, right? Number theory is perhaps, along with classic geometry, the oldest modern field of mathematics. Take that with a grain of salt. I don't really know. So the statement is, actually, I apologize. Before I write down the statement, which is something that I'm sure you've seen before, I can maybe just write it in words. So every number, people usually say except 1. It's not really very important, but every number n bigger than 1 is the unique product of primes. Okay, so let me pause the recording. So this is a statement of the fundamental theorem of arithmetic, and as you can see, there's two parts of it. On the one hand, we're claiming that every number can be factored into primes. The second part, which is the tricky one, is that this factorization is unique. Now, there's one definition that I want to write down that makes the statement a lot more clear and easier to deal with. So that's the following. So let a be natural number or just an integer, b prime. Then we define the multiplicity of a number sub that prime. This will be the biggest number, the biggest exponent k, natural number, such that p to the k divides a, right? So if you take an integer, and actually now that I think about this, we might need for this to be bigger than 0, otherwise it won't make sense, right? Okay, examples. So this is called the multiplicity. It is the answer to the question, how many times does this prime number divide this integer? So the multiplicity sub, I don't know, 5 of the number 10. How many times does 5 divide 10? Well, just 1, because 10 is 5 times 2, so there's only one 5 there, right? On the other hand, what's the multiplicity of 25? Well, 25 is 5 squared, so there's two copies, or two 5s in there, right? What's the multiplicity of 11 for sub 5? Well, that would be 0, because there is 0 copies of 5 in 11. There's no divisors of 5 in 11, right? Does this definition make sense, more or less? So multiplicity sub 2, for example, answers the question, how even is your number? In the sense, how many times can you divide this number by 2 and still get a reasonable answer? So 2, well, that's only 1. Multiplicity of 2 sub, I don't know, let's say 2 sub n. Well, this would be n, right? Okay, maybe. So that's the multiplicity. And the theorem restated, let's say, fundamental theorem of arithmetic restated, says something a lot more transparent, right? So if n is a positive number, any positive integer, then n is equal to the product of the multiplicities of n for every prime number. Right? This is a much more concise and clear way of writing down the same theorem. Here I'm saying, oh, it is some product of some unique primes. Here I'm telling you exactly what the product is, right? You can always determine this. It's the product, sorry, this is wrong. It's the product of these primes, and I'm telling you how to find the coefficient. The coefficients are the multiplicities, right? So it's p to the whatever number you get. Let's prove the fundamental theorem of arithmetic. Write down one consequence, and then we would be done with this section. There's one more section in the chapter, which we will have time to cover later, and it will be part of next week's subject as well, right? So how do we prove this? There's two parts. There's the existence. How do we know that these prime numbers exist? And there's uniqueness. So let's do these two separately. So let n be bigger than 1 or bigger than 0. Strong induction, that's right. Strong induction is used for the existence part, and regular induction can be used for the other part. So how do we do this? Well, actually, instead of using strong induction, I think there's a much cleaner way. Like I said, these are all equivalent, but maybe we can use a slightly different argument. Let me think about this. So suppose by contradiction, suppose not. Suppose these primes don't exist, right? Suppose n is the least or the smallest counterexample to the statement that is n is not the product of primes. And it's the smallest with this property, right? The well-ordering principle says if there's any number, any natural number that has a property, then there's a first natural number with that property, right? It's not the product of primes. So if there are numbers, if not every number can be written as a product of primes, well, there must be a first number that has this that has this property. So it's sometimes kind of hard to write and talk at the same time. Okay, so n is not prime because if it were, it would be a product of itself, a product of one factor. So n itself cannot be prime. So it must be composite. It must have four divisors. Sorry, it must have more than four divisors. So in particular, we can find two positive ones, a, b, smaller than n, such that they divide n, or more so, the product is n, right? But since a and b are smaller individually, then a and b are products of primes because n is the least counterexample. So a and b are not counterexamples yet. So these are products of primes. Of primes. But then if a and b are products of primes and you multiply them, well, the product is still a product of primes, right? You just concatenate all the primes that were there. Oh, but then n is as well. And this is a contradiction because we are assuming that this is not power of primes. What is this proof actually saying? This proof is just saying if you have a number and you don't know if it's prime or not, we'll just divide it by anything and you get something smaller. If what you get is prime, well, then you're done because you will always eventually hit a prime number. Otherwise, this descending chain of numbers would go on forever. But that's not possible because you started with a finite number, right? So there are no infinite amount of numbers between 0 and your number. It's only a finite many steps. So eventually you will have to hit the bottom, and that bottom is always prime, right? Every number has a prime divisor. Every number can be factored into primes, right? Another way of thinking about this is that every number has at least one divisor, so the set of divisors of a number is always not empty. By the well-ordering principle, it has a least element. And I leave to you as an exercise to show that the least element, the least divisor of any number bigger than 1, the least divisor bigger than 1 of any number is always prime. This is similar to the thing we're using. Okay, so this is how we prove that factorizations exist, but the tricky thing is uniqueness. Suppose that, how do you show something is unique? Well, we already showed that there's at least one factorization into primes, and I have to show that there's at most one. So suppose that there are two factorizations, p1 all the way to pn, and that these are the same, this is the same as these numbers, right? So you have a number that has two factorizations where all factors are primes. Right. So in particular, P1 divides, well, of course, the product that contains P1. It is already a factor of them, so of course it's going to be a divisor of them. But this is the same as this other number. So by Euclid's lemma, P1 must divide Qi for some I. Right? It divides a product, so it must divide one of the factors. Let's say that factor is Qi. Now this is something easy to prove, but since both are primes, primes that divide each other must be equal. Why is this true? Primes that divide each other are equal because the only divisors, the only positive divisors they have is 1 and itself. So P1 is definitely not 1 because it is prime. So the only explanation left is that they must be the same number, right? Now, just to frame this all in a bit more clear. Oh yes, thank you. So this is mentioned in the problem set uh, according to the chat, question 5F. Thank you, I appreciate the reference. So just to be a bit clear and not write like dot 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 when I keep going, I can just say that I'm using strong induction. And the first number that is in consideration will be the number 2, and the number 2 being prime already can only be written as the number 2, right? So base case is kind of clear. So let's say by strong induction, suppose every number less than m has a unique factorization into primes. You don't have to do this by strong induction. This is just, I'm rewriting this part so that it's a bit more understandable. And that m has 2 factorizations. What did I write here? Factorizations. That is, suppose that these two numbers are both equal to m, right? Basically, that's what I'm saying. Okay, so every number, every prime number on the left is some prime number on the right. So what we can do is just divide one by the other, right? So m divided by p1, again, this is not a fraction. This is not a rational number. This is whatever you get from multiplying p2, p3, all the way up to pn, right? So this number must be the same as the product of the qi's from I different to, sorry, that's a terrible choice for indexing, j different from I, right? So you take all primes except p1 because I'm dividing p out by p1. This number will definitely be smaller than m, right? I'm dividing by something bigger than 1, so this is smaller than m. So by hypothesis, by the inductive hypothesis, every other prime must be unique. So p1, sorry, p2 all the way to pk to pn must already have been the same as q1. There's no qi here, right? So one way of writing this would be to just eliminate it to qi. But then if I add it back, I just add back the number, then every prime on the left is some prime on the right. And analogously, every prime on the right is some prime on the left, right? So what I'm saying is all these primes are the same, just maybe written in a different order, right? I don't know if P1 is going to be Q1, maybe it's Q18, but some reordering might be necessary. This proves a fundamental theorem, right? I've proved the uniqueness and the existence. The factorization exists and the uniqueness. Now, it might be challenging to prove the uniqueness if you don't know Euclid's lemma. And that's an interesting thing to think about because it tells you that uniqueness is somehow more special, more dependent on the natural structure of the integers than existence. Existence is kind of more trivial. And it is true that in other types of rings, recall that the integers are a ring. I didn't define ring, I defined semi-ring, but then we proved that every element, every integer has an inverse, namely minus itself, right? That forms a ring, not just a semi-ring. And in rings in general, it is easier to find this factorization into primes, whatever those things are, but uniqueness is special. Many rings don't have unique factorizations. So this is kind of a stronger property. We need more structure about about the integers for uniqueness than we need for existence, which explains why uniqueness was so much harder, right? Here we had to use Euclid's lemma, which it was a corollary from a theorem, and that theorem was discovered much later than all of this. So there's a lot more theory in the uniqueness part. Now, maybe we can do some examples just to clarify this of how we would apply the fundamental theorem. So every prime number is, of course, just a product of itself. Maybe you can find the number 15 would be 3 times 5. I don't know, number 56. How do you factor the number 56? So to factor it, you iteratively divide by some prime number that you find that divides the number, right? So this is an even number, so you divide it by 2. And if you divide it by 2, you get what? 28. So you divide it by 2 again, and then you get 14, and then you divide it by 2 again, and then you get 7. And 7 is prime, so you just write it down as part of the factorization, right? And you can do the same for many things. So in other words, the multiplicity of 56 mod 2 or sub 2 is 3. That's the exponent. And here's a remark. The greatest common divisor between two numbers, if you were to factor this number into primes, how do you think this is related to the factorization of A and the factorization of B? And if you think about this, it's actually not too hard to see that if you just multiply over all primes, then this is the prime, and you take the least multiplicity, right? So this is why I find this notation with the multiplicity so much nicer, right? It adds so much information to what you're doing, so much clarity. So I don't know why this isn't more standard among textbooks. Similarly, the least common multiple, as you might expect, will be the maximum instead of the minimum, right? To prove this, you just have to show two things. First, that this is a common divisor. It will be true because if you take the minimum of the exponents, in particular, it will divide the larger one, right? Whichever one is larger. So this is definitely a common divisor. Why is it the greatest one? Well, you cannot really go any higher than this. And I leave this remark to you. This is actually a nice exercise. So maybe I should just say this is an exercise. This can easily be generalized to more than just two numbers for the greatest common divisor, right? And there's this analog for the least common multiple, which is just the maximum. So do spend some minutes thinking about this, and it will greatly improve your understanding of the fundamental theorem of arithmetic. And it gives you a very neat formula of computing the greatest common divisor if you're given the factorization. For small numbers, this is much quicker than the Euclidean algorithm. For large numbers, this is much slower than the Euclidean algorithm because we have to find all these primes in the first place. And the only way of doing that is basically dividing a bunch of numbers, right? So the Euclidean algorithm is a lot quicker for finding greatest common multiples in general. But for small numbers, it might be quicker to factor this. Example, and I will address the question in the chat in just a second. So the greatest common divisor between 56 and 15 would be what? Well, 56 is already factored up there. So what I do is I just copy down all the prime numbers that factor either, right? All the other prime numbers will always have an exponent of 0, so I don't even bother writing them down. This is something that is interesting. So this product might seem like it's infinite because it's iterating over all primes, but most primes have 0 as an exponent. So this is okay. It's always a finite product. What is the smallest thing that I have to write up here? Well, it's between 0 and 3, smallest of them being 0. What about 3? Well, it's between 1 and 0, so the smallest is 0. What about 5? It's also 0. 7 is also 0. Oh, this is 1. And if you scroll up to I think the example that we did in class of the extended Euclidean algorithm, we got the same answer, but this was way quicker than applying the Euclidean algorithm because we already had the factorization. Okay, so this is a good question. What does P prime refer to? P prime means that I'm multiplying over all primes, right? P is just any prime number. So this product is a product over all prime numbers. So let me add this. Maybe I can add this at the beginning of this part, right? So that's a good question. In the meantime, one funny consequence of the fundamental theorem of arithmetic is the fact that there are infinitely many primes, which is something that is not obvious, but it was known for a really, really long time. There are other consequences, but they will only be relevant once we know more about fields and other types of structures because they have to do with things beyond the integers, right? So here's the notation. Hopefully this helps clarify this. So the notation is what I mean by p prime is you take the first prime number, which is 2, and then you find its multiplicity sub 2 of n, right? Then you take the next prime number, which is 3, and then you take the multiplicity of 3n. And then you take the next prime number, which is 5. Then you take the multiplicity 5n. And then you take the next prime number, which is 7. And this goes on forever. You do this for every prime number. Now, the reason why this is well defined is because you could only ever have finitely many prime numbers that divide your number. So eventually, these will all be 0, right? So these will all be 0. P, I don't know how to write this. Let's say P1, P2, 0, and so on, right? And these are all 1. So they don't affect the product anymore. You only ever have to worry about finitely many primes. If you want to save time, of course, it's not every prime that you consider, only the primes that divide n to begin with. But those two products are the same. So yeah, do spend some minutes thinking about this, review these notes, make sure that it's clear. In the next class, I will mainly address questions about this and maybe continue with the next topic, but make sure that this is clear. I am not giving you too many results, too many theorems or facts or examples, because these are, in my opinion, enough to understand most of the theory. But you do need to spend some time digesting this, right? It's not just memorizing this formula and then it will work. You do have to spend some time writing your own examples. Maybe let's just do this corollary. There are infinitely many primes. Something that hasn't been mentioned at all, and it's very neat, and I'm sure you've seen this proof 1,000 times. It's one of the first things that people prove ever. Okay, so suppose that P, many people do this proof by contradiction. There's no need, right? Suppose that P is a finite set of primes. Right? I'm not assuming anything, right? No contradiction. I'm just taking a finite set of prime numbers. So then define n as the product of x, where x is an element of p. Just multiply all these primes together, right? So clearly, and this is something that is proved in the problem set as well, if I'm not mistaken, any number and its successor, or said otherwise, consecutive numbers are always coprime, right? Consecutive numbers are always coprime. So n and n plus 1 are coprime. So no element, no x in P divides n plus 1, right? N is divisible by everything in P because it is the product of everything in P. So if I'm saying that n plus 1 is coprime with it, it shares no divisors except 1, well, then nothing in P can divide n plus 1. because they don't share anything. They don't share any divisors in common. And the divisors of n are precisely the elements of P, right? So no element of P divides n plus 1. So by fundamental theorem of arithmetic, and we actually don't need the strong bit, the uniqueness bit. We only need the existence bit. By the fundamental theorem of arithmetic, there is a prime, right? It has a factorization to primes, so in particular, at least there's some prime P that divides the number, right? N plus 1 is definitely bigger than 1. So, okay, is a finite non-empty maybe. Okay, so if it's not empty, then n plus 1 is definitely bigger than 1. So it must have a factorization into primes. So just pick any prime, and that prime p divides n plus 1. There is a prime dividing n plus 1. Okay, this is just the uniqueness bit. But then p, lowercase p, is not an element of capital P, right? Because p is a divisor of n plus 1, and I just told you that no element of p divides n plus 1. So in particular, lowercase p is not an element of P. And then we're done, right? Because then no finite primes contains all primes. No finite set of primes contains all primes. In other words, the number of primes must be infinite. No need for contradiction. I asked ChatGPT to write down this proof for me and insisted and gaslit ChatGPT into telling me that this number plus 1 is always prime, that the product of primes plus 1 is prime. And ChatGPT would say, oh, yes, you're right, this number n plus 1 is always prime. That, of course, is not true. You can easily find counterexamples to it. But my point is, yeah, don't use ChatGPT to make your assignments. Maybe when it's good enough to work, you can just cheat your way through it. But right now it doesn't, right? And also you will not learn, which is the whole point of doing this. Okay, any questions? I will stop the recording.